Alright, so in this video I'm going to show you the polarity of molecules and how to find that. I'm going to use a website called ChemDL360. You can use it if you want to. I think it'll help you visualize some of this. Alright, so the first molecule we're going to look at is carbon dioxide. It's already up on the screen. I wanted to get the browser working before doing this. So carbon dioxide, if we draw the dot structure, it has 16 valence electrons, and if you draw it, it looks like that, right? So it's linear, it's a straight line. That's the Vesper theory structure. And so now if we look at this molecule closer, you can see that's what it looks like, right? And I should be able to move this around. There we go. All right, and you can see it from any direction. And I can show you the bond dipoles. So we can look at these. We know that this molecule has a dipole on the bonds, right? So you can see that this bond is polar going out towards oxygen, and this bond is polar going out towards that oxygen, and we can look at the partial charges, right? Let me turn this so we can see it. So this negative 0.51 is on that oxygen, this negative 0.51 is on that oxygen, and 1 is in the middle. And so if I get rid of that and turn on the molecular dipole, for crying out loud. And turn off the bond dipole. See, it doesn't have any molecular dipole. Up here it says 0, dipie. That's the unit we use to measure the actual dipole. So there's no dipole on that, and it's because it cancels out. You have this one pulling this way, and you have that oxygen pulling the electron density that way, and so overall in the whole molecule it cancels out. Alright, so the next one that I want to do is going to be water. Okay, so next I'm going to look at water. Let's see if it works this time. Alright, so the next shape we're going to look at is water, and water has 8 valence electrons. So we have oxygen in the middle, and I've explained in class that it's probably better to draw it like this so that you can see the shape of it. So since the steric number is 4 with 2 lone pairs of electrons, it is bent. And if we look at the model here, you can see, oh no, okay, you can see that it's bent in space, and I can rotate this around. Hopefully it'll let me. There we go. And so we can see the bond dipoles, and as you can tell, the dipole is being pulled. There's a thing going down the hallway. It's gonna get really loud. Sorry. The dipole is being pulled towards the oxygen because oxygen is more electronegative. And then if we look at the molecular dipole, oh, I have the wrong thing. If we look at the molecular dipole, you can see that the molecular dipole is up this direction. Let me see if I can make that a little bit. Why does it do that? Oh, a little bit smaller. So you can see that the bond dipole goes up towards here. That's basically the sum of these two. They're called vectors. So it's a pulling motion or pushing motion, and if we add those two together, it would be right here in the middle, and so it just goes upward. All right, so next we're going to talk about formaldehyde. I write it, oh, it shouldn't be H2CO3, it should be H2CO. So let me Let's wiggle that out. And so H2CO would have 2 plus 4 plus 6, that's 12 valence electrons. And carbon will go in the middle, and it's going to have 1 oxygen and 2 hydrogens. And so right now I have 2, 4, 6 electrons, and then I'm going to go to the outer atoms, 8, 10, and then 12. And carbon needs 1 more bond, so these electrons are going to come over here and form a double bond there. So I'm going to get rid of this. And that's what it looks like. And so since the steric number on the central atom is 3, and it doesn't have any lone pairs on the central atom on carbon, then it would be trigonal planar. And I know that this bond right here is polar, and it pulls this way, while the carbon-hydrogen bonds are nonpolar. So if I look at my structure right here, I need to bring this to the front. There we go. We can see the bond dipole. It's going to do its thing, sorry. So I can turn this way so we can see it sideways. The bond dipole, there's not really much of a dipole on the carbon-hydrogen bonds, but there's a large dipole on the carbon to oxygen bond here going this way. And we can see the molecular dipole as well. It's even greater than water. You can see the dipole up here in the corner if you're curious. It pulls very heavily towards the oxygen, and so the whole molecule itself is polar that way. So we would know that the whole molecule is polar towards the oxygen. So this shows the dipole moment. And we put this plus sign at the end to show the positive side, and the other side is negative. So we could actually even put this side is partially negative while this side is partially positive. And we can look at that if I wanted to show you guys the electrostatic potential map. You can see that here. The red indicates a negative charge and the blue indicates a positive charge. So you can see that down here on this end, the negative charge and the positive charge on this end, that means that the molecule itself has an uneven distribution of electrons and would carry a negative charge on this end and a positive charge on this end, which makes it interact differently with other molecules. So that's why polarity is important. All right, sulfur trioxide. So we have 24 electrons here. Sulfur would be in the middle, oxygen, oxygen, oxygen. So there's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So all of my electrons are out. Sulfur needs another bond. So I'm going to put these electrons here like that. And then I can erase those there because they're not there anymore. And so again, this is going to be trigonal planar because it has a steric number of 3 without any lone pairs. All right, and this time though with the trigonal planar we have oxygens on all of the ends. And so I know that this looks like it looks different in this structure here, and it's because we don't cover things like formal charge, and formal charge will add more steps to how you draw these structures, and I don't want to overwhelm anybody, so I tend to not go over that too early. Otherwise, it gets way too confusing. But we do go over it more in AP chemistry. So you just look forward to that if you're going to take it. But for the most part, you can still get whether or not a dipole is, you can get the right structure with the way that we do them. And so it's a good starting point. Okay, so this is sulfur trioxide. It really does have 3 alternating double bonds there. The bond dipoles they're pretty strong. We've got, whoa, we've got one that goes up this way, and one that goes up this way, and one that goes up this way. And so since this molecule is flat, right, it's flat, they all cancel out because the sum of these two, whoops, the sum of these two right here would be going this way, the sum of these two would be going this way, and the sum of these two would be going this way, and so it cancels out. So there is no molecular dipole here. It's 0. See up here in the corner? It's measured in dBi. That's what we use to measure the dipole moment. So the bond dipole, let me get rid of that. And see, there's no molecular dipole. I still have it check marked, and it doesn't show up. All right, next we have CH4. So CH4 is going to look like this. Or I'm sorry, CF4. Might as well be CH4. It's just not as bad for the environment and smells pretty terrible. Okay, and it's going to be 4 bonds, no lone pairs, or 4 is the steric number, no lone pairs, and so that's tetrahedral. Blah, blah, blah. And when we look at this model, just move it all out of the way. Whoa. No, I want to do this. There we go. Okay, we can see the bond dipoles. They're pretty big. They're very big. Because it's carbon-hydrogen bond, and so we would expect it to be big. But if you were to look at it on a molecular dipole level, it would be 0 because they're all going to cancel out. So let me put these bond dipoles back in there. These two right here that are pulling out this way, they're in the same plane, and so the sum of them would be going that way. And then if we flip it around so I can see the bottom here, these two down here coming out this way, the sum would be going down. So they would end up canceling out. Anytime you have a molecule that has all 4 of the same or all of the same substituents on the outside, and there are no lone pairs on the central atom, it's going to be nonpolar. The lone pairs don't make it polar, but it makes the molecule unevenly distributed because it's got a lone pair somewhere instead of another atom. So that's one way you can look at it. Okay, next we're doing CHCl3 or chloroform. So chloroform will have carbon, hydrogen, and 3 chlorines. All right, so that's 21 and 4, 25, 26 electrons. This is also going to be tetrahedral, but instead of comparing it back to the CF4 one, this has hydrogen on one end, right here, and so I wanted to show you what happens when they're not all the same. Okay. And so the bond dipoles don't look correct on here. They should be going with the chlorines, I think. And it's just drawn wrong. I don't know, it's very strange. All right, so let's look at the molecular dipole. It's going down here because these chlorines are pulling the electron density down, and so it's going straight down. And the dipole there is 1.3, so it's a little bit less than water because these are chlorines and not oxygens or fluorines, but it's still significant. All All right, next we have PCl5, and so I'm going to put 5 chlorines on here, and this would have 40 valence electrons. So each of these has a full octet. And phosphorus can go past the octet rule because it's in the 3rd period or lower, so it's fine with those 10 electrons. And because it has 5 bonded atoms and no lone pairs, it's going to be trigonal bipyramid. Oops. Or trigonal bipyramidal. So I can pull this over here. All right. And if we look at it, is it gonna let me move it around? There we go. So you can see the trigonal planar thing in the middle. It kind of looks like a jack, toy jack, right? Jacks. You have these two, so it would be polar going towards, the bond would be polar going towards oxygen on every single one of these bonds. But since it's trigonal planar in the middle, that would cancel out, and then it's linear on the top and bottom. Those are they're called axial positions, and then these are equatorial because they're along the equator. They would cancel out as well. So if I look at the bond dipoles here, you see they're going along the bonds. That's what the chloroform one should have looked like. And then if we look at the molecular dipole, though, it's so insignificant because 0.0002 might as well be 0. So you can see that there's nothing really here, right? Okay, so let's look at the next one. We have SF6. This is sulfur hexafluoride. Sulfur hexafluoride is a pretty cool compound. It's heavier than air. If you've seen any of those experiments online where they have the fish tank filled with a gas and they have the little boat riding on top of it and they fill it up with a gas and it sinks, that's sulfur hexafluoride. And just like helium makes your voice get higher when you inhale it, sulfur hexafluoride makes it get lower. So it's a pretty cool thing. But anyways, so if we look at the bond dipoles, they're going to be big because fluorine is very electronegative, right? And so here we go. Come on. So you can see how they cancel each other out, and they're so long. Those lines are so long because the polarity is so high in those bonds. I'm trying to make it bigger on your screen so I can pull it out a little bit. So these arrows are so long because these bonds are so polar, but you can see how they would cancel each other out, right? I mean, because it's a square in the middle, a plus sign, and then the top and bottom would cancel out as well. So when we look at the molecular dipole, it's 0. There's nothing there pulling anything. All right, I've got 2 more. So here we have SO2, sulfur dioxide. So we have sulfur, oxygen, oxygen, and so that's 2, 4, 6, 8, 10, 12, 14, whoa, 14, 16, and there's 18 electrons here. So sulfur needs another pair of electrons. These are going to come over here and double bond. So I can get rid of this down here. Why won't it let me? There we go. Won't let me get rid of those electrons. So I'm going to scribble them out. Okay, so this is going to be bent. It has a steric number of 3, right? And 1 lone pair. And so now if I look at my molecule here, it's bent. You can see that it's bent. And all right, and I can look at the bond dipoles. Maybe. All right. So you can see that it is pulling towards the oxygen like usual, right? And so the sum of these two going down, with the way I have it set up here on the screen right now, it would be right in the middle. And so my molecular dipole is right in the middle, going downward. And it's because it takes that bent shape. If this was linear, like the very first example, carbon dioxide, we wouldn't see that. And again, the reason it has two double bonds here is because of formal charges, which is something we're not talking about right now. So that would not necessarily be correct to write down on the test. I expect it to only have one double bond for you guys. All right, and the next example is NH3. I left the dipole on, look at that. Okay, so NH3 is going to look like this. And it's going to be trigonal pyramid. And so, because it has a steric number of 4 with one lone pair. And if we look at the bond dipoles, nope, don't want that, I want this. There we go. Okay, they're all pulling up along those bonds towards nitrogen because nitrogen's more electronegative than hydrogen is. And so if we look at the molecular dipole, it's going upwards. And it's pretty significant. It's almost as much as water. All right, so that's it. So I expect you to be able to draw these little arrows either along a bond for a bond dipole or to show the polarity of a bond, and to be able to show the polarity of a molecule by showing the molecular dipole. We're not going to calculate these values up here, but I do want you to be able to show whether or not the molecule overall is polar and which direction the dipole is going. And one last thing, if you want to be able to look at these on your own and play with it, there's also some games and stuff on here for memorizing ions and elements and stuff. It's a pretty interesting website. It's ChemEd.dl, the Chemical Education Digital Library. And so I just Google ChemEd.dl or ChemDL360, and it'll bring it up. It'll be one of the first links. All right, good luck.